Hi, this is T3, Day 1, Introduction to Integrals. So just a quick recap. In the first trimester, we talked about the definition of the derivative and that it's really just slope, that it's the instantaneous rate of change, slope of a tangent line. So instead of being like algebra 1 where the slope we just had to look at a linear equation, we could look at a curve and say, well, at some point on the curve, what would be the slope of that tangent line? So in the first trimester, we developed just the definition of the derivative using that change quotient and the limit as h went to 0, the distance between the 2 points went to 0. We also talked about in the second trimester, we developed the shortcut rules. And then at the beginning of the new year, we started doing our related rates program problems and also the max and min program problems. So we were able to use our derivative and apply the problems there. So now we're going to undo those derivatives. We're looking at integrals, and we're going to develop that concept as we go on over the next couple of days. So one of the first things that we want to remember is if we have a basic function, we'll call it the s of t, our distance function. If we take the derivative of that function, we get the velocity. Derivative of distance is velocity. If we take the derivative of velocity, which is the second derivative of distance, we get acceleration. And we've talked about those being sort of the layers of an onion, that if we have distance, derivative goes up to being velocity, the derivative of that goes up to acceleration. When we take the antiderivative, the underderivative of acceleration, we'll get back to velocity. When we take the antiderivative of velocity, we'll get back to distance. But we're getting ahead of ourselves a little bit there, but that's where we're going. So let's look at a problem that we did back in September, where we looked at a distance function, and you were asked to describe the velocity of that function. So the problem that we did back in September is a car is moving and the distance is given below. Find the velocity at time equals 2. Okay, so we're given at time 0, we know that the car has traveled 0 feet. At time 1 second, the car has now traveled 10 feet. At 2 seconds, it's traveled 25 feet, and etc. When we wanted to find the velocity in feet per second, thinking about what our units are going to be, feet per second, we were looking at a rate of change. So we would find the slope, the rate of change. If we're interested in finding at t equals 2, we'll find the slope 25 minus 10 over 2 minus 1, 15 over 1, or 15 feet per second. And the slope here, 45 minus 25 over 3 minus 2, is 20 over 1, or 20 feet per second. If we want to get our best guess, we'll take the average of those two. We'll say, all right, well, the average is 15 plus 20 divided by 2 is 17.5 feet per second. So again, that's just a review from a problem we did back in September. Our new example, though, is suppose a car is moving and has a positive acceleration, so it's continuing to get fast. We're not told that it's a constant acceleration, just that it is positive. It doesn't slow down anywhere. It is getting faster little by little, or it could be getting faster a lot and then faster a little, but it's continuing to get faster. The car's velocity is given in this table below. So at time 0, the car is traveling at 20 feet per second. At time 1 second, the velocity is 30 feet per second, and etc. Now we want to know how far has the car gone after 4 seconds. Well, we don't really have a process for this yet. So what we want to do is we want to say, well, what if we look at just this first interval of 1 second. During that 1 second, the slowest that this car might have gone for most of that second is 20 feet per second. The fastest that it might have gone for most of this 1 second interval is 30 feet per second. So if we just look at that first interval, that first 1 second interval, this car might have gone 20 feet per second for 1 second, which would be 20 feet. It's also possible that for most of that interval, the car could have gone 30 feet per second for that 1 second, going a maximum possible of 30 feet. Well, we don't know whether it was a constant acceleration. We can't say that, well, it was 20 seconds at the beginning, 20 feet per second at the beginning of the interval, and then it increased consistently up to that 30 feet per second, or whether it stayed at 20 feet per second and then just before it hit the 1 second mark, bam, it went up to 30 feet per second, or very, very, very gradually up, or whether it went up pretty fast. We don't know. So the best we can do is just say, well, we have a lower estimate or an underestimate, or we have an upper or overestimate. So we know during that first 1 second interval, the car traveled somewhere between 20 and 30 feet. Well, if we look at the second interval, we know that looking from here to here, the slowest that the car could have gone for most of that 1 second interval is 30 feet per second for 1 second, which would be 30 feet. It's also possible during that interval that the car could have gone 30 feet per second for most of that interval of 1 second, which would mean that it would have traveled 38 feet. So again, during that interval, that second interval from t equals 1 to t equals 2, the car traveled somewhere between 30 feet and 38 feet. In the third interval, the slowest that the car could have gone is 38 feet per second for that 1 second interval, which would give the car a distance of 38 feet. It's also possible during this interval, the fastest it could have gone is 44 feet per second for that 1 second interval, giving us a distance during that 1 second interval of 44 feet. And our last interval, our fourth interval, which is from t equals 3 to t equals 4, the slowest that the car went during that interval is 44 feet per second for 1 second. 44 feet per second times 1 second gives us 44 feet. Or the fastest that it went during that interval is 48 feet per second. So we want to assume the fastest for that 48 feet per second for a 1 second interval is 48 feet. So we don't know. Again, we don't know whether the car increased slowly and then got up to speed, or whether it quickly went up to speed from 44 to 48, or whether it just traveled up at a constant acceleration. We don't know. But we do know for this last interval that the car traveled somewhere between 44 and 48 feet. Well, if I add up the distance that it traveled in each of those intervals, I get 132 feet. And if I add up these intervals, I get 160 feet. So what we can say is that our actual distance is somewhere between 132 feet and 160 feet. This being the least possible, that being the greatest possible, and I'm using less thans instead of less than or equal to, because we know that it has to be something slightly more than that 132 feet and something slightly less than that 160 feet. And I'd like to just observe the difference here. If I take that 160 and I subtract 132, I get 28 feet as my fudge factor. That if I wanted to side with the person who was really conservative and said, oh, I think it was the slowest here at 132 feet, the furthest they're off in their actual measure is as at most 28 feet. So their error, their accuracy, how far could they possibly be off? The difference between these two values is 28 feet. Okay, so now let's scroll down. This is what I just wrote up above. Now let's look at this graphically. So what we've got here is I put the 0, 20 on here, 0, 20, 130, 238, 344, and 448 on this graph. So this is our velocity in feet per second. This is our time in seconds. So if I want to look at what I just did above, but graphically, what we're saying is that this car, I want to assume, if I'm being conservative and I want the underestimate, I'm going to say that for that first interval of a second, that the car traveled at that 20 feet per second. If I take that 20 feet per second for this entire 1 second interval, and I take that 20 feet per second on here, and multiply it by that 1 second, well, I'm getting the area of this rectangle. And the area of the rectangle is the 20 feet. So we see that the area of this rectangle represents the distance. Cool. My second rectangle, I'm going to say, all right, well, for the second interval, let's just say that he went the slowest possible of that interval, which is the 30 feet per second. So I have another rectangle, the area of which feet per second times second gives me the distance. The area of this rectangle represents the distance traveled during that interval. In the third interval, I again have a rectangle whose height is 38. Its width is 1 second, so I get the 38 feet. And my last interval, I'm going to say that the car is traveling at 44 feet per second for 1 second. And I again have a rectangle whose area represents the distance traveled. But what if I want to assume the greatest speed for the interval? Well, then I'm going to assume that the rate of travel is 30 feet per second during this first interval. So the area now is this higher rectangle. In my second interval, from t equals 1 to t equals 2, I'm going to say, well, it could have gone close to 38 feet per second, which would give me this rectangle. And in the third interval, I'm going to say, I'm going to use this higher number, the 44 feet per second. So I end up with this rectangle. And for the last interval, I'm going to say, well, he could have gone close to 48 for that entire time. So I've got that rectangle. Well, the space that's in dispute is this region right here. Did he really go 20 feet per second, or did he really go 30 feet per second? He went somewhere in between. So the difference between traveling 30 feet or 20 feet is this shaded red area. And in the second interval, might have gone this distance, might have gone this distance. And again, we have a disputed area and a disputed area. If I take this rectangle and just shift it over here, I just want to have a look at it over here. So we'll take this rectangle and put it over here. And I'm going to move this rectangle over here. And I'm going to move this rectangle over here. I'm going to move this rectangle over here. So let's just say I'm sliding this guy over here, sliding this guy, so that I can stack up all these little disputed areas. Well, the height here is a height of 48. The height here is a height of 20. So the height of this entire stacked rectangle is 28. The width of this stacked rectangle is the 1 second, and this is 28 feet per second. So the 28 times 1, the area of the stacked rectangle, is 28 feet. That's the area that we call our disputed area, our questionable accuracy, the error. How far off could I possibly be? And that's the 28 feet. Okay, so a few things that I want to have a look at, and these are pretty important things for you to have. We have 5 values in our table of values, but how many intervals do we have? We have 4 intervals. Well, we're going to call n the number of intervals. And in this case, our n is 4. How wide each interval is, how long is each interval, the delta t, the change in time, in this case is 1 second. Well, let's see where we're getting that from. We're going to call this our A value, our beginning time value. This is our B value, our ending time value. This is f at A. What is our y value at A? What is our y value at B? If I want to know my delta t, I can take my B minus my A and divide by the number of intervals. So 4 minus 0 divided by 4 gave me the 1. So this is an important equation we'll want to come back to. And the other is that if I rearrange this, if I multiply each side by n and then divide each side by delta t, I can say that n is equal to b minus a over delta t. So another important equation to have. All right. So that was interesting. We get that the error is 28 feet. Well, if I want to be more accurate than that, I'm going to send my researchers back out to have a look at this car again. And instead of just measuring every second, I'm going to say, why don't you take these measures every half second and see if we can't be a little bit more accurate. So let's look at this lower estimate. We'll look at both a lower and an upper estimate, but for right now, let's just start with the lower estimate. Well, in this first interval, I'm going to say, well, that's going to be at 20 feet per second. 20 feet per second times 0.5, because now our interval is only a half a second wide, plus 26 times 0.5, plus the lower number here is 30 times 0.5. And the lower number here is 35 times 0.5. And then the lower number here, 38 times 0.5. Lower number here, 42 times 0.5 plus 44 times 0.5. And lastly, 46 times 0.5. Okay, so I'm going to put a little star here. Sometimes when people get going here, they just want to put all of those numbers on there. We want to remember that we're just looking at the interval, and on this interval, the lower number is 46, so we're stopping there. To make this a little bit easier to calculate, we could factor out that 0.5, and then I just have the 20 plus the 26 plus the 30 plus 35 plus 38 plus 42 plus 44 plus 46. So this is still my lower estimate. If I add up these numbers, the 20, 26, 30, 35, 38 on my calculator, I now have 0.5 times 281, which gives me 140.5 feet traveled. So coming over to my graph, that's the area of that rectangle, plus that rectangle, plus that rectangle, and that one, and that one, and that one, and that one, and that one. So how many intervals do I have now? 1, 2, 3, 4, 5, 6, 7, 8. So my n equals 8. My delta t, how wide is each interval? Each interval is 0.5. My a value is 0. My b value is 4. My f at a is 20. My f at b is 48. If I wanted to calculate my delta t, I mean, I can see how wide it is, but if I wanted to calculate it, I could say that delta t is b minus a over n. Delta t is equal to 4 minus 0 over 8. Delta t is a half, or 0.5. And then also the reverse of that is that my n would be my b minus a over delta t. N is equal to 4 minus 0 over a half. N is 8. We can see that by counting it. Okay, well now let's come back over and we're going to do our upper estimate. The upper estimate is going to be 26 times 0.5, right here, plus 30 times 0.5, plus 35 times 0.5, plus 38 times 0.5, plus 42 times 0.5, plus 44 times 0.5, plus, this is 26, it looks like a 0, plus 46 times 0.5, and plus 48 times 0.5. Well, if we like this line better than this line, we could have gone to that immediately. That I know the width of each rectangle is 0.5, and the height of the first rectangle is 26. of the second rectangle is 30, of the third is 35, the fourth is 38, the fifth is 42, the sixth is 44, and then 46, and then 48. And again, don't just get carried away listing all of the numbers. We want to consider that that is the first interval, the width of the first interval, the width of the second interval, and the height at that for that rectangle. Sorry about whatever just flashed up there. So again, if I want to come back to how am I going to make this easiest, I want to recognize that this list of numbers is very similar to this list of numbers, except this one has a 20 and it doesn't have a 48. So if I want to quickly add this up, I can take this 281, subtract the 20, and add on a 48, and I can see that that number is now 309. 309 times 0.5 is 154.5 feet. So what we're adding up here is the height of the area of that rectangle, and 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 then this rectangle. And again, we have some disputed area. Did they go as much distance as the green rectangle, or just as much as the blue rectangle? And in between are these little areas that may or may not have gotten traveled. If I pull all of these red rectangles off to the side and say, well, there's one of them, there's another one, I'm just sliding these over and stacking them up. There's a third one. I'm going to bring this guy over and this guy over, bring this one over, and that, and then this one. Well, if I stack those all up, the height is again going from 20 up to 48. The height is still 28 feet per second, but the width now is only a half a second. So the total area in dispute, my error, my accuracy, if I'm going from, it would be the 28 times 0.5 is only 14 feet. Here I can say my actual value must be something greater than 140.5 feet, but less than 154.5 feet from these two values. And the difference here is 14 feet, so my error. What I'd like to point out here is that this 48 is our F at B. So I can take my F at B, and then I subtracted my F at A. How tall is this? Well, it's F at B minus this F at A. And then I multiplied that by how wide is this rectangle. This equation is what we're going to call our error equation, or our accuracy. We're going to fine-tune this a little bit and say that we're going to want the absolute value of F at B minus F at A times the delta t, just because if this had been a decreasing function, I want to make sure that this the height of the rectangle stays a positive value. So if F at B happens to be a lower number than F at A, I would want to make sure that this turned into a positive. So our error, or our accuracy, this 14 feet, can be found by F at B minus F at A, take the absolute value of that, and then multiply by delta t. Down here below, I just have these solutions typed out more clearly. And in particular, I have the graph showing them pulling together these red boxes and sliding them over to here. These are the examples from up above, but just typed out and shown more clearly how we're doing that. So instead of my hand-drawn graphs, you can see what's going on here. So hope that helps, and we will continue on with this with T2, day 2. Bye-bye.